since then is working with Jack Vanis' group in University of Edinburgh. And of course, Jack Vanis is a TRR member, and Hossein is also now part of TRR PhD panel. And we will hear from him today about efficient computation of Lagrangian limit. So all yours, Hossein.
Thank you very much. Hi, everyone. Very glad to be here. Thank you, Manita and Karsten, for inviting me. And got it. And also Jennifer and everyone else for coordinating this talk and also my trip. So today I'm going to talk about, my original title was Grid-Based Computation of Lagrangian Mean, and this project has gone beyond grid-based, so I used efficient computation of Lagrangian mean to be more inclusive. The first few slides I want to give you some motivation. So basically this is about time averaging, and we know time averaging is one of the most essential tools we have in atmospheric and oceanic sciences, because we can make meaningful inferences from observed data using time averaging. We can also use time averaging to post-process numerical simulations. You can also say, in a sense, time averaging is hidden in any numerical simulation because we don't resolve all the time scales in our numerical models. So in a sense, we are time averaging. This is even more highlighted considering the fact that there are two time scales in geophysical fluids. One is the slow one associated with vortices and eddies and jets, and then the fast one more associated with waves. And we can use time averaging to decompose the flow to like slow part and a fast part. Most of you probably know there are two types of time averaging in geophysical fluid dynamics. One is the Eulerian mean, which is basically sitting at a fixed spatial point and then measuring our variable and averaging the time series of that variable. And then there's another way of averaging by following particles along its trajectory and taking the average along the trajectory of the particle. To give you a better feeling, I just want to show you a movie. It's a very simple 2D flow, and I put a dot here. I measure vertical vorticity at this point in space, and also follow a particle that starts from this point in space and measure the same quantity along the particle trajectory. As you can see, these red dots are the trajectory of the particle started from black dot. But to the right, I'm showing you the time series of vertical vorticity measured at this fixed black point, and then the red one is the same quantity vorticity along the particle trajectory. And then if I take the average of the top panel, the black one, that would be my, it's hard to use all the tools, my Eulerian mean, and if I take the average of the bottom one would be my Lagrangian mean. And if you're familiar with fluid dynamics in 2D incompressible flow, vorticity is conserved along the particle trajectory. That's why you just see a straight line, so it doesn't change as we move along the particle. In the next few slides, I want to make a case that Lagrangian averaging is much more powerful than Eulerian averaging. One of the reasons is Lagrangian averaging is probably our most reliable tool if we want to separate the wave and non-wave part in oceanic submesoscale or atmospheric mesoscale for two reasons. First of all, the spatial scales of waves and like other components are very similar, so we can use spatial filtering to do the decomposition. If you use like time filtering or just Eulerian time averaging, it is not still very successful because we have Doppler shift when we have very strong background flow. So the frequency of wave that we observe on like fixed point in space is the sum of intrinsic frequency, this omega, and then a Doppler shift term. And depending on this Doppler shift term, the observed frequency could be much lower than the intrinsic frequency. So the time scale of observed waves, the observed time scale of waves could be very close to the slow time scale of eddies and vortices. So sometimes we don't manage to do very good filtering based on Eulerian averaging. This is an example from a study by Shakespeare et al. They took a part, the part that I'm showing is a part of Southern Ocean downstream of Drake Passage. These are, I think, kinetic energy of Lagrangian mean quantities and Eulerian mean quantities. As you can see, the Lagrangian mean version managed to remove the waves much better than the Eulerian mean version, where the wave signals are still there. And that's because it was a very strong like stream background flow here, which Doppler shifted the frequency of the waves. Another reason for the superiority of Lagrangian mean, which I'm more excited about, more as a theoretician, is how Lagrangian mean includes the wave feedback on the flow very naturally. To explain this, I just use like a sketch of geostrophic balance, and the argument is a lot more general than geostrophic balance. Let's say we use Eulerian averaging and decompose our flow variables to a part that has a mean and a part that is the fast part, doesn't have a mean, its mean is 0. So I showed with bar and then prime for all the variables. If we scale our equations properly and consider that u prime is smaller than mean u, then we get geostrophic balance that probably everyone's familiar with. In case that u prime is not much smaller than u bar, then this term remains in the equation, which is the mean of the quadratic wave components, or the primes. So it doesn't go away, and if we want to have like even just this slow dynamics, we need to include this wave feedback. And in different contexts, people have given this different names, like you can see it as a derivative of Reynolds stress, or meteorologists like to see it as gravity wave momentum flux. They're all the same, but somehow people want to include it to have better representation of waves on the flow. GLM theories, or theories based on Lagrangian mean, actually somehow automatically include that wave feedback without an extra term. So they claim that the geostrophic balance continues to hold in the presence of strong waves, but for Lagrangian mean quantity. So it has this form now. So now this, if you work it out, this expression somehow inside it has the wave feedback that I talked about in my previous slide. So it's much more powerful formulation, because we don't need to do a decomposition and then take care of the mean of the quadratic terms of wave components. Now we have it all in one go. And here, I mean, I'm standing on the shoulders of giants. Like, there's been a lot of theoretical work back in like 70s and 80s and up to now. If you really want to see like a simple derivation of this wave average geostrophic balance, you can just go to this recent paper that we worked on. Geostrophic wave average geostrophic balance is just one example. A lot of reduced models have this Lagrangian mean naturally showing up in their formulation. For example, if you look at the Shea-Vanes model of near inertial waves, at the end it's expressed in terms of Lagrangian mean. So the take-home message here is what is left after Lagrangian filtering is more self-contained or sustainable dynamics. Is more useful than what is left after Eulerian mean. So the question is, now that somehow you're convinced Lagrangian averaging is very important, why don't we use it all the time? The reason is computational difficulties. It's not as straightforward as computing the Eulerian mean. And I tried to show different difficulties that come with particle tracking, which is the traditional way of calculating Lagrangian mean. We track particles and calculate the mean along the particle track. So just to explain what kind of difficulties show up, let's go back to particle tracking. We have a sketch of grid points. What we do in particle tracking, we seed our particle at, let's say, a grid point here, and then use the velocity field to add vector particle forward, find the position after, let's say, a time step, and then at the new position, we interpolate for both, using the neighboring point, for both velocity and the quantity of interest, let's say temperature here. And then we take more steps forward. So along this particle track, now we have the values of temperature that we can take average of. This is like forward particle tracking. We can do it backward as well. So we take one step backward, find the position, and so on. There are a couple of, again, challenges that comes with this particle tracking. If we do forward particle tracking, particles may get clustered in one region. So at the end, we don't have very good representation of Lagrangian means. Some parts are very sparse, some parts are very jammed. If we do backward particle tracking, we don't have that issue, but we need a lot of memory space because we need to save velocity and the field of interest at many snapshots in time and all over the space. So it has a very big memory footprint. We also, it's computationally a bit demanding because we need to interpolate for both velocity and the quantity of interest. The other issue is, it's a real headache when it comes to parallel processing. And I try to explain again with this sketch here. So let's say this is my computational grid. I divide it to some subdomains and I assign each subdomain to a processor, which is working more or less independently and in parallel. And I solve an equation on each subdomain. If I want to track my particle in each subdomain starting from my grid points, the particles may cross one subdomain and go to another one. Considering that each processor is working more or less independently, once a particle crosses one subdomain, goes to another, that processor needs to pass information to the new processor to track the particle. That communication between the processor is quite time-consuming and slows down the whole process. The other issue is a lot of particles may accumulate in one subdomain, so the processor is taking care of the middle subdomain, has a heavy load compared to the others, and this load imbalance slows down other processors considering that they need to work synchronously. So my goal in this project was to come up with a grid-based method that calculates Lagrangian mean without tracking particles, which seems to be contradictory, but I'll explain to you how we can do that. To get there, maybe I should clear up some definitions and notations. Let's say the quantity we want to take the mean of is f, and it's defined over the space x and time. Can be temperature, can be velocity, vorticity, whatever. And then the Eulerian mean can be defined simply as this integral, which is 1 over the averaging interval over the value of f at point x during this interval, the integral of that. The Lagrangian mean, I use a bit of a weird notation, but it's quite useful. I use this psi of tau and x and t. When it comes to Lagrangian averaging, I'm following a trajectory, so I need to label that trajectory. And this x and t are the label of my trajectory. So if my particle crosses point x at time t, I use that as a label, and then psi gives me the position of particle at any time tau, but for which particle? The particle that is at position x at time t. So basically now my Lagrangian mean is the calculation of psi, which is the particle position at time tau, over the averaging interval. So
can you do this for centered things?
Okay, so yeah, it's a very good question. I wanted to get back to that. So once I calculate this, I can map it to any other points. It's the best way to, the best point to assign the Lagrangian mean to, as Carsten mentioned, is the mean position, and best point in time probably it's the half of the interval. So mapping to different time interval is very easy. We just find the value, say this is for time t minus t0 over 2. For the position, we need to calculate the mean position as well, and then assign the value to the mean position. But once we calculate the Lagrangian mean and the mean position, we can do that, which is an extra step, but it's quite crucial. So my grid-based Lagrangian averaging, which I refer to as GBLA, is centered around the idea of partial Lagrangian means, which are basically Lagrangian mean up to a point, let's say tk in time, which is somewhere between my averaging interval. So it's not through all the interval, it's just up to point tk at my grid points. Again, at the moment I'm using the label at time point xi, which is the end position of the particle during that interval. So the core idea is to iteratively update these Lagrangian means. If we know the Lagrangian means of all the particles that end up at our grid points at time tk, we want to find the Lagrangian mean of new set of trajectories that end up at our grid point again, but at time tk plus 1. And the Lagrangian mean is extended from t0 to tk plus 1 instead of from 0 to tk. I'll explain this better in a figure. Probably my last sentence was not very clear. So let's say these are my grid points, xj, xi, xp, and xl, and I know the Lagrangian mean of all the trajectories that end up at my grid point at time tk. So I know the Lagrangian mean from t0 all the way to tk. And as I said, this is an iterative method. Now I want to find the Lagrangian mean of new sets of trajectory which start from time 0 and end up at my grid point at time tk plus 1 this time. And I showed one of them with this red color here. So in a sense, I don't follow one particle. So at each time step, I switch from one set of trajectory to another set of trajectory. And then how do I do that? I do that by splitting the Lagrangian mean, or this extended Lagrangian mean, to two parts, a part from t0 to tk and a part from tk to tk plus 1. So at first step, I find the position of the particle on this red trajectory at time tk, which I don't know, using the velocity at grid point xi and time tk plus 1, just advecting backward. So I get this point yi, and then I know that I can find the Lagrangian mean in the first bit, highlighted with orange, by using the available Lagrangian mean in the neighboring points, these blue trajectories from t0 to tk, and then I can approximate the second bit with a numerical approximation. Again, I'll go into more details, hopefully it will be clear at the end. So let's say the first step, I run my simulation, I calculate f, which is my quantity of interest, at time tk plus 1, on all the grid points, and also my velocity on all the grid points. I don't know what this I is, typo here. So my goal is to, and also know the Lagrangian mean of f up to point tk. And my goal is to find the Lagrangian mean of f at all the grid points up to point tk plus 1. First, I just advect my particle backward, as I said, using the velocity point at the grid point. So I'm just considering one grid point, which is xi. So I get yi. And then I write the definition of Lagrangian mean, which was that integral I showed you previously. 1 over the averaging time interval, which is now extended to t0 to tk plus 1, and then the integral of f along the particle trajectories. And then I split the integral to two parts, a part from t0 to tk, and a part from tk to tk plus 1. And I do like multiply and divide by tk minus t0 to get this form. And I did one more thing here. So instead of using xi and tk plus 1 for the label of the particle, I use yi and tk. It's the same particle. The particle that passes passes through the point yi at time tk is the same as the particle that passes through xi at tk plus 1. So this integral has a nicer form. So this bit here corresponds to the journey of the particle from t0 to tk, and this pink part is the journey of the particle from yi to xi.
Hossein, there's a question from Knut, maybe directly to your...
Yeah, sorry, Jennifer, I didn't want to interrupt.
No, I don't need to track all the particles at all. So I start from my first step, and I do this backward advection. So at any step, I use a different set of trajectory. Maybe at the end, I'll go back, maybe I can have a conversation with Knut, so it wouldn't be interrupted. Yeah, so basically then the first integral is nothing here than the Lagrangian mean of the particle that ended up at yi up to point tk, and I can calculate this Lagrangian mean here using the neighboring values of Lagrangian mean that I already know. And for the second bit here, this integral, considering my time step is short, I can use trapezoidal rule to just approximate it with this value, which is the value of f at y at time tk and the value of f at xi at time tk plus 1. Then I tried to test my, my algorithm on several examples, and I'm quite convinced it's working. I show you some of the results. This is just a 1D synthetic flow, has like a fast component and slow component, and then I just integrate it in time. To the left, I show you the Lagrangian mean velocity using particle tracking with very high resolution and using my grid-based Lagrangian averaging, or GBLA. They really lie on top of one another. And then I tried to also see if my method converges. So I used very, very high resolution particle tracking as the truth, and then looked at my algorithm with linear and cubic interpolation. So the red one is the cubic interpolation, and the black one is linear interpolation. Both are converging. Then I went to a 2D flow. If you remember from my early slides, vorticity is conserved on particle trajectories in 2D incompressible flow. I can use that as an advantage, as a fact, to know the value, the exact value of Lagrangian mean, which is the instantaneous vorticity field. So to the left, I'm showing you the instantaneous vorticity field, and then I expect my Lagrangian mean to be the same as that. And I started with two like sign vortices, and at some early steps, I'm showing you in the right panel, and then much later is the bottom panel, or bottom row. So as you can see at early times, and then, sorry, the middle column is my GBLA with linear interpolation, and the right column is my GBLA with cubic interpolation. At early time, which is the top row, even linear interpolation does a very good job to capture the Lagrangian mean. And then much longer averaging period, linear interpolation starts becoming inaccurate, but cubic interpolation is still quite accurate if you compare by eyes. If you, what?
Is there no friction? What is it?
So for this one, there is no friction, but I made my time steps very short to be able to. It becomes very unstable later, as you predict, but this one doesn't. Yeah, as Carsten said, if there is friction, the vorticity is no longer conserved along the particle track.
Can you explain what you mean by linear, or what do you interpolate?
So in this, So if I go back, in this step that I calculate the Lagrangian mean at y, I need to use an interpolation using the Lagrangian mean of the particles that end up at grid points.
To better understand this, can you sketch the algorithm, what you do from time to time, step to step?
Okay, the first step, from your model, you get the values of f, let's say it's temperature, and velocity at next time step. Okay, so from tk you go to tk plus 1, you get velocity and temperature. And then the second step, using the velocity at the new time, you go backward in time, calculate the position of yi for all the grid points. And then the third step, you calculate the Lagrangian mean of the first bits of the red trajectories using interpolation. And then the fourth step, you calculate the second part of Lagrangian mean by calculating temperature at yi at time tk, and then you have the temperature at xi at time tk plus 1. So you get the second term, and then you add these terms. So it's kind of like a, oh sorry, there's 1 over tk minus t0 missing here. I need to correct. This is the first time I'm giving this presentation. There's a typo here, but if you go back to my paper that I mentioned later, it's correct over there. So it's kind of like a weighted sum of these two parts. So I have this part plus that part. And then there's an extra step. I don't want to confuse people, but since Carson mentioned, you should do this for mean position as well, to get the mean position, to map it back to mean position.
Does it somehow depend on grid size?
Yes, the interpolation depends on the grid size. And this stepping back depends on the time step. If you make the time step shorter, this approximation, this integral would be better. If you make spatial grid point finer, then this interpolation would be better.
In the next slide, you test this impact of delta x.
Yeah. I have tested as an effect versus delta t as well. So if you look at my paper, it's very thorough investigation there.
But for the full calculation of the Lagrangian mean, you also use the same delta x. So is this a...
Yeah, no. Yeah. So let me go to the next slide I explained to you. So here I'm just being more quantitative for the 2D flow. To get the truth, my exact solution, I use very fine resolution and particle tracking. Okay? But to compare particle tracking with my method, then I have the same delta x for both of them to have fair comparison.
And then, does it compare well?
Yeah, so this is the plot. So here, this particular case of 2D flow, I was lucky because vertical vorticity is conserved, and I can use the instantaneous value for vertical vorticity as my exact solution, and then I use approximated Lagrangian mean and use this error norm. So the blue one here is the particle tracking. The black one is my GBLA with cubic interpolation, and the magenta is GBLA with linear interpolation. I mean, overall for this case, the errors of particle tracking at the beginning were lower than GBLA, but when I lowered the delta x, they converged. Also, the rate of convergence of GBLA was even faster than particle tracking. The version with linear interpolation still has higher error, but it's convergent. In the remaining time, I want to just talk about one application of my algorithm and maybe finish the talk. And as I mentioned, there are a lot of theoretical studies claiming that in the presence of strong waves, geostrophic balance holds better for Lagrangian mean quantity instead of Eulerian mean quantities. I tried to investigate that using this algorithm. So I took like an anticyclone. This is just a 2D shallow water simulation. And the height field is the equivalent of pressure field if it is scaled properly. And I had like a very strong point cloud wave going through this vortex. And then I calculated the Lagrangian mean Coriolis force, which is F cross UL, or Lagrangian mean, and Eulerian mean Coriolis force, which I'm showing you with the black dots here. So everything in the left panel is Lagrangian mean, everything in the right panel is the Eulerian mean. And then magenta arrows are pressure gradient or height gradient, sorry, this is still a typo, for Lagrangian mean and Eulerian mean. So as you can see, in the Lagrangian mean version, the height gradient or pressure gradient perfectly balances the Coriolis force, but there are some regions in the Eulerian mean version that, that the pressure gradient and Coriolis force don't balance each other. So it really shows the power of Lagrangian mean here. So for conclusion, I tried to compare I came up with a method to calculate Lagrangian mean without tracking particle, which in comparison to particle tracking methods has several advantages. It's more memory efficient. I don't need to take time series or all the variables in time. I just need few fields in 2 time steps, and I iteratively go forward. It is potentially less computationally demanding. Why? Because if I'm not calculating the Lagrangian mean of velocity, I don't need to interpolate for velocity fields. Because in particle tracking, you need to interpolate both for velocity and the quantity of interest. And it's a lot more parallel processing friendly, because I don't track things, particles. I can sit on grid points and update things. So things are more or less inside one processor. And whatever I do to pass information between the processor for the simulation, I can do it with Lagrangian mean values. GBLA can be affected by interpolation error more than particle tracking, as one of my convergence results shows. So using better interpolation or finer grid guarantees an accurate result. I've shown temporal and spatial convergence of GBLA numerically, but I haven't proved it mathematically. And as an example or as an application, I showed wave geostrophic balance. I investigated wave average geostrophic balance with this method. If you want to read more about this method, you can go to this paper that is recently published. I want to mention a few things as future work. My applications were all on 2D flows. The next step would be taking this, implementing in a 3D model, and use it to study wave mean flow interactions. We can potentially use GBLA for subgrid parameterization. If you go back to the beginning of my talk, Lagrangian mean has already the effect of wave feedback. So if we Lagrangian filter things, whatever is left is just the fast things that we usually want to get rid of or dissipate. So if we just dissipate the Lagrangian fast components, or the components that is left after Lagrangian averaging, then we can contain the dynamics with better approximation and for a wider range of scales. We can improve the Lagrangian filtering by adding a kernel to the definition of mean. So lots of people, particularly the study that I mentioned, Shakespeare et al., they don't use the very simple definition of the mean that I used here. They take the time series of a variable along the particle trajectory and do low pass, high pass filtering in Fourier space. We can do the same thing just by adding a kernel to the definition of mean. And then at the moment, I'm working on the continuous version of this method. So we can, instead of the algorithm, we can just solve a PDE, which gives us the Lagrangian mean, which happens to be this PDE. So if we solve this PDE over an averaging interval, we get the Lagrangian mean. And my algorithm is just special discretization of this PDE, like a semi-Lagrangian discretization of this PDE. In some models that we have like periodic boundary condition, we can just solve this PDE pseudospectrally, which doesn't need any interpolation anymore, so it can be very accurate. Again, depends on the model. This can be very useful. If I have a few minutes, I want to mention a few things considering Karsten's question. So not everyone is familiar with generalized Lagrangian mean theories, but general Lagrangian mean theories are saying the best form of Lagrangian mean is the Lagrangian mean that is assigned to the mean position, not any label of the particle trajectory. To do that, as I mentioned, with this version of the algorithm, we need to calculate the Lagrangian, the mean position, and then map whatever we calculated, because everything now is defined in terms of the end position, back to the mean position. I came up with another version of this algorithm that directly gives you the Lagrangian mean in terms of mean position, which will show up later. Thank you very much for paying attention to my talk. For people here, I also maybe want to mention one more thing. At the moment, I'm working on a new numerical method to solve a kinetic or wave action equation, something that Karsten's group, some people doing the IDEMIX. It's just a new, it's a numerical method that hasn't been used in this context, and I've got some interesting results. It's just really work in progress, but if you're interested, we can talk about it at some point, considering that your group is also working on this problem. Thank you very much. If there are any questions, I'll be happy to answer. Particularly, Knut, if you want to elaborate on your question online, maybe I can make myself more clear.